Now, when we say global warming, that doesn't just mean that the average temperature of the Earth is going up. It does mean that, it is going up. But it also means that that warming is almost global. It's taking place almost everywhere. This diagram shows temperature trends for roughly the last 100 years. Positive trends are in the warm colors, the yellow, brown, red. Negative trends are in the cool colors, gray, blue, down to purple there. White is little or no change. And what we see here is that probably about 85 or 90% of the map is showing a warming. There are a few places that show cooling. That cooling tends to be relatively modest. A number of places showing rather large warming, the interior of the continents in Asia and North America, especially up towards the Arctic, although there are a couple of patches where cooling is taking place, like here in the North Atlantic, here in South America, this particular part of Africa. These gray colors mean that there aren't enough observations to determine the trend. They tend to be in places where there aren't a lot of people living and certainly not a lot of weather stations. So when we talk about global warming, we are talking about a phenomenon that we're seeing almost everywhere on the Earth. As it turns out, in the southeastern United States, the trend over this period has been relatively small. But again, remember the distinction between weather and climate. The reason why this pattern isn't entirely uniform is partly due to random variations in the weather. So we wouldn't really expect to see this trend pictured in such a way that the color would be the same throughout the map. And I'll show you some results very shortly illustrating why this is. Computer models are certainly very important. And when we talk about climate models, what we're talking about are very complex computer programs that attempt to represent all of the processes that are happening in our climate system, on the surface of the Earth, in the atmosphere, in the ocean, and the interactions among all of these different components of the climate system. So in order to do that, we have to capture those processes in the form of equations that we can include in our computer program. For some of them, it's very straightforward. It's like F equals ma that you learned in physics class. But in other cases, our understanding is still developing, and so we have to try to include those processes as best we can. We do that. We write these complicated computer programs. We run them on very powerful computers. In fact, many of the most powerful computers in the world are dedicated to the task of running climate models. Another big use of those powerful computers is running the kinds of models that are used by meteorologists to make weather forecasts. And then these are the models that we use to look back at what's happened in the past and to try to understand the causes of those past changes and to look forward to see what's coming. An interesting slide here. I'm about to show you a little movie. Before we start the movie, I want to tell you what it is. This is a projection of the changes in temperature from one particular model. It happens to be the model that's run at the laboratory where I used to work down the road in Princeton, New Jersey, the NOAA Geophysical Fluid Dynamics Laboratory. Up here in the upper right, you see a year, and that counter is going to change from 1970 to 2100. And as it changes, the colors on the globe here will change, showing variations in air temperature either above or below the average for the period from 1971 to 2000. And since this slide was produced for a general audience, the units here are degrees Fahrenheit instead of degrees Celsius, as we would expect to see in more of the scientific diagrams that I've been showing you. And so where you see a yellow patch, that means the temperatures are warmer than the 1971 to 2000 average for that location. Where you see a blue patch, they're colder. And what I want you to pay attention to once we start this slide is how those patterns of colors change, both from year to year and then over the long haul. So Saj, if you would start that up. Okay, so you see things kind of going back and forth from blue to yellow. But gradually, as we go on, you see things are becoming more and more yellow. That doesn't mean that blues don't pop up once in a while. That's weather. So just because it's been warm lately, that doesn't mean the world can't have a relatively cool year. But gradually, as we go on, now if you look at North America, we're seeing a lot of red. So by now, the cool years are yellow, and the warm years are red. The continents warm up faster than the oceans. There are a couple of interesting spots in the ocean that don't warm up very much at all. Maybe we could run that one more time. And so watch, you see that here the weather is varying from mildly cool to mildly warm. Every now and then it turns yellow out here. That's an El Nino happening in the model. You've all heard of El Nino probably. But over time, we see this inexorable change where more and more of the map becomes yellow. More and more of the continents become red. Now, if you look over North America, you're not even seeing any white anymore, let alone blue. And so this is how we make projections of how the climate will change in the future, using the output of models such as these.